Here. So today I want to talk about classification of six-dimensional supersymmetric conformal field theories and little string theories. So let me write down the aim of these three lectures. And why are we interested in these theories is that there is is widely believed that these are the only UV complete supersymmetric theories in 6 dimensions which do not involve dynamical gravity. So throughout these talks, I will discuss various classification programs for such theories. So we believe that these theories have a special class of vacua, which are known as a tensor branch of vacua, on which the theory becomes a non-abelian gauge theory coupled to some tensor multiplets. So I will describe what these tensor multiplets are. So you can bootstrap your way from IR to UV to describe these theories. You can look at what are the consistent tensor branches that can arise in these theories and try to classify them. That is one approach. And the other is directly try to look for these theories inside string theory or F theory by taking some decoupling limit of string theory vacua.
Are you going to focus on maximally supersymmetric? I mean, how much?
All supersymmetric. So
what about zero supersymmetrics?
No zero supersymmetry. At least some supersymmetry.
The conjecture is that there is none.
None what?
Non-supersymmetric CFT.
No, I mean there might be, but I'm not claiming that in the conjecture. I'm saying about supersymmetric theories only. Yeah, but we don't know any examples, non-supersymmetric examples. Okay, so let me start by reminding you something about supersymmetric algebra in 6 dimensions.
Sorry, can you tell us a little bit the content of this conjecture? What would be a similar statement in other dimensions? For example.
Now 6 dimensions is something special because you can classify them in F theory.
No, but I usually think of UV complete theories as some sort of a UV fixed point, and that's already a CFT there, right? So it seems like a.
No, I'm saying.
It seems like a tautology unless the definition.
No, I'm saying UV complete quantum field theory. A quantum field theory which makes sense in UV, so it does not have any problems.
UV fixed point.
Yes, so there is a UV completion of the quantum field theory. Your scattering amplitudes, your correlation functions make sense at any energy scale. There is no cutoff. That's what I mean by UV complete.
But by definition, it has to be a fixed point, right? Because
in the UV, you might have a fixed point, in which case it will be a CFT, or it might be a quantum field theory, or it might be a little string theory.
Yeah, a little string theory is not a fixed point.
Mm-hmm. No, but in other dimensions.
Other dimensions,
Is the statement just that? I mean, okay, little string theory, yes, but in
So
general, that's what you would expect, right? If the theory is UV complete, it's a CFT in the UV.
Yes.
Yeah, but because he's including little string theory, he has some sort of broader framework in mind. Anything that makes sense that doesn't involve gravity, I think, is what he has in mind.
So I'm talking about quantum field theories, not CFT. So there is some energy scale. It can be a CFT. CFT is an example of a quantum field theory, but you can have asymptotically free theories, right? In 4 dimensions, you can have asymptotically.
I mean, that's a CFT in the UV, right?
Yeah, but in the IR, it's a completely different theory. So I want to describe the whole theory as one unit.
No, but actually, just the context. In the context of actually real, genuine quantum field, like little string theories don't have a stress tensor. So in some sense, you might say they're not quantum field theories.
Right, but yeah, I'm saying UV complete theories, not quantum field theories.
But if you look at just quantum field theories, what Abhijit is saying is the usual law, that all quantum field theories in the deep UV are either free or the conformal field theories.
Right.
I mean, free are
Conformal.
Well, there are some free theories that are not like free angles in 3 dimensions.
Oh, I
not
see.
conformal.
I see.
It's better to leave it.
right? So,
Yeah.
so when I say theory, I talk about the whole unit from UV to IR, the whole theory at all energy scales. So this conjecture is saying something, something very concrete, right? It's saying that you have these SCFTs, but there are no marginal or relevant deformations of these SCFTs. You cannot get quantum field, non-conformal quantum field theories out of them.
Say that again, please.
That there are no non-conformal UV complete supersymmetric quantum field theories in 6 dimensions.
Okay, that's about
There are-
operators, marginal
Yeah.
operators.
There are no, but you have relevant operators, presumably?
No relevant
No
operators.
supersymmetric.
Supersymmetric.
Yeah.
I see.
That's the non-trivial.
This is part of the conjecture, is it?
Yes. So this conjecture is a very big conjecture, and
So then it follows
I
that
don't-
you can't have in the infrared some SUSY theory in 6 dimensions, which might have a mass scale and so on, at all. I mean, in that, or rather,
No.
as an effective theory, yes, of course, but that could have arisen from a UV complete theory.
that can arise from a UV complete little string theory if it has a mass scale.
It can
Little,
arise.
yes, little string theories are not conformal, they have a mass scale. I will describe little string theory soon.
Okay, so they could arise from that, but they could not arise from a UV complete field theory.
Yeah, not from a
With
local
the stress
local
tensor.
local field theory. Yes.
I see.
Well, unless they got supersymmetry accidentally in the end.
Okay,
Yeah, that could happen.
Yeah.
some higher dimension operators might take it.
Yeah.
Interesting.
Okay, so let me start by reminding you about supersymmetric algebra in 6 dimensions. So the Lorentz group is SO1, 5. Let me write down algebras throughout this talk. So this is the
So just one question along the same lines. When we say that in an SCFT, a six-dimensional SCFT, there are no relevant operators, marginal relevant operators, which preserve supersymmetry, is this a representation theory statement?
it's a dynamical statement.
Not just, that doesn't follow just
I mean, sorry.
just doesn't follow representation theory.
Yeah, I think it can follow from, but you need to know what is the consistent
I'm looking
SCFTs.
for, let's say, scalars,
Ah,
scalar
I see,
operators, which obey unitarity bound, which preserve supersymmetry in 6 dimensions. And the statement is that there exists none from representation theory. Is that true?
No, I don't think it's a representation theoretic statement. Yeah.
But if representation theory allows it, you could add it to the Lagrangian also.
Somehow, the dynamical statement is that in the spectrum of operators, there is no such operator,
Yeah.
even though it may a priori exist. So that would be some
Not there
dynamical
in the
statement.
spectrum.
Yeah.
So, very subtle.
Yeah.
I see.
Yeah, I'm not sure, but there is this paper by interrogator Dumitrescu, Cordova, which tries to argue about the statement that relevant and marginal operators don't exist. But I think there is some dynamical statement. They have a mostly representation theoretic statement, and then they boil down this problem to checking statements about 't Hooft anomalies, and then they show that in all F theory, all the SCFTs that have been found in F theory do not satisfy these properties.
I see.
So
And
it-
what about non-SUSY marginal or
Yes, thank you.
relevant operators? Are they present? You starting from a UV supersymmetric 6D CFT, do you have marginal or relevant non-supersymmetric operators that are in the theory, as in you could? have
There could be, but we don't know examples.
No, there are.
Yeah.
Like, what about the symmetric traceless XIX, M5 brain theory?
Uh-huh.
Look at the symmetric traceless scalars. Those are dimension 4.
Mhm.
They're there in the theory. The chiral primaries, right? You can just add them.
So this is the Coulomb branch operators.
They're the analog of trace phi I phi j,
Mhm.
symmetric traceless under. I mean, they're trace phi I phi j.
Yeah, these are the Coulomb branch operators.
In any case, yeah, I see.
Right, but
I mean, we know they have dimensions by supersymmetry. They're there. The dimension 4, they exist.
they don't deform the theory. They're not relevant or marginal.
They're relevant because they're dimension 4.
Yeah, they'll give masses to some.
Okay.
And they don't, adding them to the Lagrangian doesn't preserve supersymmetry.
Okay. So you're not saying it's a supersymmetric operator?
No,
Okay.
my question was about
Right,
SUSY breaking operators.
I see.
Right.
I see.
Okay. So in 6 dimensions, we have a Lorentz algebra. And then I'm allowing myself to have 2 kinds of R symmetry algebras. Let me index them by M and N. Sorry. Okay, and I will use some indices. Alpha range from 1 to 4, mu range from 1 to 4. And these are indices for SO1, 5 complex spinors. So if you look for spinor representations of SO1, 5, you find 4-dimensional representations which are self-dual, but they are not real. So they include invariant antisymmetric tensors. And let me denote them by omega alpha beta and omega mu nu for these 2 representations. So you can use these tensors to map the representation to the dual representation.
The R symmetry is 2 pieces.
Yes, 2 pieces of R symmetry. So this will be for n equals to m comma n super algebra.
And if you make it super conformal,
Then there will be restrictions on m and n.
yeah, one of them is 0.
Okay.
Sorry, I didn't understand your indices. Alpha is 1 to 4, and what is mu?
Mu is also an index which goes from 1 to 4. This is the other spinor representation. There are 2 Weil spinors. Okay. Okay. And I will use.
And these invariant antisymmetric tensors. Sorry, what does that? I should know this, but what does that mean?
They are invariant under SO1, 5 action, and they are antisymmetric. And for the USP2M and USP2N, I will use indices small I and capital I. These are USP2M and USP2N vectors.
So sorry, these invariant tensors I should again know, but I'm not. So suppose I forget the 1, 5. That was SO6. Let me imagine. Then what is this tensor? This is 2 spinor indices, huh?
Yes.
So 2 spinor indices. So
Is this the 6? I mean, they're antisymmetric?
it's 3.
They are antisymmetric.
So can I write this as?
SU4.
But for SO6, the complex conjugation takes you from one to the other, I think.
This fundamental times anti-fundamental equals 1. I mean, the singlet piece in the fundamental times anti-fundamental of SU4, right?
Okay. Yeah.
I see. I see.
But the complex conjugation works differently here. That's why both.
I see.
I see.
Yeah. So you're saying the spinor of SO6 is like fundamental of SU4, and
Yeah.
fundamental times anti-fundamental gives you identity. That's
Yes.
okay. Fine.
Sorry, that will be the delta symbol, right? That will be the tensor which takes you from the complex conjugate to the dual representation. Yeah.
I thought it's invariant tensor, so I thought
It's also an invariant tensor, but it's a different one. It's not this one.
Yeah, can you tell us in SU4 language?
So this is a pseudo-real representation, right? And every pseudo-real representation admits an antisymmetric.
Okay, that's great. But to just
Sorry.
so the spinor of SO6, let's say a chiral spin of SO6, is a fundamental of SU4, like Kapijit said. So you're saying built out of 2 fundamentals of SU4, I can make an invariant tensor.
Of whatever is the analog of SU4. Because
Yeah.
SO1, yeah.
Let's forget the reality stuff.
Yeah.
Okay, we worry about reality. Okay, so is this the statement that out of two fundamentals of SU4 I can make an invariant tensor?
Yes.
How can you do that?
Isn't it putting the gamma matrix in there?
I mean,
That
you
is-
cannot do it
this
with
is a
SU4
six.
because SU4 there is no, it's not self-dual. The spinor representations are not self-dual. Complex conjugation takes you from one to the other.
So that must be what he's saying, right? From a spinor and an anti-spinor.
Yeah.
You can.
Isn't
There
this
is no
six
anti-spinor.
dimensional, right? Sorry, can I ask you? Omega
Yeah.
is 6 dimensional, right? What is the dimension of that representation? The antisymmetric thing?
Yes, so it's 4 by 4, 4 times 3 by 2.
Yeah, 6, right?
Yes.
So I think it must be just the vector of SO6. You can make from fundamental or anti-fundamental.
But then you should have a vector index. This object here has only two spinor indices and is invariant. If it was an object with two spinor indices and a vector index, then it would be a gamma.
Actually, this is not like that. It's not.
It's
not
just
that
two
Yeah.
spinor
appears-
indices,
It's 2 spinor indices.
and it's supposed to be invariant by itself.
It's not like it's a vector which appears in this product.
Ah.
Sorry.
So he's saying that there's basically the Klebsch-Gordon of two of these things
Right.
contains
Contains
the
a-
singlet.
So it must be then that it's a singlet. Yeah, sorry. Okay.
So it must be that what Abhijit is saying, right? That is the fundamental times anti-fundamental after you take the reality into account. Because that's the only way you can get a singlet.
Yeah, it must be that. Okay.
But then I'm confused that you have a second one. Because there should be a unique one, right?
No, but there are two of them.
Is the other,
Two is the anti-fundamental times fundamental
oh,
inside
that's
it.
confusing.
But I mean, just in group theory, there's only one way to make a singlet out of.
Yeah.
There's no way to make a singlet out of two fundamentals. There's no way to make a singlet
Yes.
out of two anti-fundamentals.
Mhm.
And there's only one way to make a singlet out of fundamental and anti-fundamental. Now there's some
So-
complex conjugation here. That's what's
Yes.
going on.
Yes, so I think this is anti-fundamental times fundamental.
And that must
And this
also be-
fundamental times
must be like
anti-fundamental.
real part of it and imaginary part of it or something like that.
I see.
I mean, so
In the complex group, there's only one thing. Do you agree?
sorry, in the SO6 case, yes. Then the complex conjugation takes you from here to here.
And there would be only one invariant tensor with two indices.
Yes. That will
There's some
be
real and imaginary.
alpha mu.
Hmm?
In SL4.
In SL4, yes.
SL for
That's a fully complexified thing.
Yes.
So here the, yeah, so
even SU4 with just
SU4,
complex
yeah.
coefficients. Okay, whatever. I see. And so these omegas are real objects. Is that right? Or how do you think? Or they go to each other under complex conjugation. How do this go?
no,
These
under
two
complex,
omegas, how do they behave?
Yeah,
under
exactly.
complex
That's the
conjugation?
question.
it will stay same. It's a
Same,
real
it
object.
stays.
Yeah.
Okay, so it looks
It's,
like
it's not a, yeah.
Okay.
Two real.
It's not
Yeah.
exactly real because then you can make your representation to be completely real.
But the data is a real tensor.
Yes.
Fine. So
It's a Majorana kind of object
yeah.
rather
So
than
you combine
strictly
them
real.
together, the data is that of one complex object.
Yes.
So that makes sense.
Yeah, okay.
Okay. So I will use the small I and capital I to denote USP vectors, and they have their so there are invariant tensors associated to USP2M and USP2N vectors as well. Again antisymmetric, and let me write them with epsilon as an epsilon.
But also there are two types, alpha beta type and mu type.
No, this is one. There's a USP2M vector gives you this, and USP2N vector gives you this one.
I mean, so this thing is USP4, right?
USP2M. So this one, I'm talking about the R symmetry now.
Yeah. No, but over there you had two things.
Yes, that was for SO1, 5 spinor representation, and this is for USP vector
But
representation.
SO1, 5 is USP4.
Yes.
So fine.
I mean SU4.
Sorry. Yeah, no. Yeah.
Okay, so now combining them, combining
So these invariant tensors also are to index?
yes, but this is the vector index now
Vector of SP.
of USP.
So just like that was a vector of SU.
Yeah, so if you were in SU2, USP2, then this will be just the standard epsilon symbol for SU2. Okay, so combining these invariant tensors, you can write down a Majorana condition.
This is the familiar J symbol of SP, right?
Right.
Absolutely.
Right. Okay. Got it.
So So I can demand that
Yeah,
my
the metric for SO.
Mm.
right, so I have some supercharges which are going to, I should first. So I have two kinds of supercharges in n equals to m comma n, and their indices are q alpha I and q mu I. So they have some chirality with respect to SO1 comma 5, and one of them transforms under USP2m, the other under USP2n. The complex conjugates are also there, so I also have q bars. Okay, and now I'm proposing that you can actually combine the q bars with the q's using a Majorana condition.
Sorry, I missed this. Q's are the supercharges, isn't it? Or did I miss something?
Yeah, q's are the supercharges. So, to start with, the alpha representation was not real; it was self-dual, and similarly for the I representation, it was self-dual but not real. And when you take a tensor product of them, you get a real and self-dual representation. So you can make it, so it's a strictly real representation. You can combine q's and q bars together. And in terms of these invariant tensor, it looks like this. So this is the complex conjugate of qi alpha, and I can first make the complex conjugate representation into the dual representation, and then use my invariant tensors to combine it with q. So delta is another invariant tensor which allows you to which makes dual representation and the complex conjugate representation isomorphic.
What people normally call C for spinors, right? It's like a charge conjugation, right? Charge
Yes.
conjugation.
That's what you said.
Sorry?
The omega which he has, that is like the charge computation.
Yeah.
Omega. Well, the way I'm familiar with this condition is to write q star is equal to C and then this other invariant tensor for epsilon times q. There's a way of writing it that looks like that. So
Okay.
there must be some ways of combining these into C.
Delta alpha bar alpha times omega alpha beta
Is the C, yeah, probably.
Okay. And similarly, I have a Majorana condition for the other supercharges. So in effect, we have a total of 8 times m plus n supercharges. And the supersymmetry algebra takes the following form. Here P is the momentum. So I can get the momentum either as an antisymmetric product of one of the chiral spinors or antisymmetric product of antichiral spinors. And this is the n equals to m comma n SUSY algebra.
I'm sorry, what is P? Some kind of projection?
P is the momentum.
Oh, moment, sorry, of course.
Yes.
Is it vector bispinors?
Got it.
Okay.
And what about the q with the other q?
Yes, it's this.
No, qi with q.
Yeah, that's 0.
What about a central charge? You're not allowing central charge?
No central charge right now.
Why?
I mean, there are central charges, but okay, let's see. I'm just not sure how to write it. What are the things which should appear on the right hand side?
Some Zij, some Zii,
Right. And
and then
out of these two,
elements are built out of those.
Sorry, no, even
there
in
is
the
no.
first line, there would be an omega.
Maybe the central charge is only in the first
First and second.
line, yeah.
There's an omega alpha beta piece. Zij omega alpha beta piece.
Yeah,
Okay.
that's right.
It's more natural.
Yeah,
Zij times symmetric.
yeah. Maybe the other one shows.
It should be, under simultaneous exchange of alpha, beta and ij, shouldn't the right hand side be anti-symmetric?
Yeah, it is antisymmetric. All of these are antisymmetric.
Okay, so omega alpha beta was symmetric under exchange of alpha and beta.
It was antisymmetric.
Okay, and Zij is,
Antisymmetric.
Therefore, it will be antisymmetric. You choose
Yes.
your central charge to have the right property.
doesn't that make it symmetric? It should be symmetric. But the Qs will exchange with the.
Yeah, they are symmetric. So there's an antisymmetric times antisymmetric.
It's fine. Z will be antisymmetric, right?
Oh, right, right. Yeah, thank you. I got mixed up.
Thank you.
Uh,
And
Okay.
in fact, on the Coulomb branch in the M5 brain theory, you do have these central charges, right?
yes,
So, yeah.
the strings carry the central charges.
Yeah.
Okay, so now there's a result due to NAM that only n equal to m comma 0 can be extended to, or n equal to 0 comma n, to a superconformal algebra. And now since we are interested in superconformal field theories, there is a result due to Cordova.
So basically, one of the two has to be 0.
Yes,
And parity will switch which.
yes, parity switches them.
So it doesn't matter which.
So there's a result that for m greater than equal to 3, you do not have a stress tensor multiplet. So if we are looking for SCFTs, then we are restricted to n equal to 1 comma 0 and n equal to 2 comma 0 for SCFTs. This has been proved. And there are examples of both of the cases.
You are dropping the central charges now? Or keeping it?
No, I'm not dropping any central charge.
Superconformal field theories have no center.
Yes, so they are getting dropped.
In the case of SCFTs, those have to be 0. Yes. Those are scale.
In the conformal vacuum.
In the conformal.
Yes.
Sorry, and okay, so this is a nice sophisticated theorem, but at a lower level, if you just, even without conformal invariance, you just want a free theory. If you want the existence of a free multiplet without spin, with spins, all spins less than equal to 1, that will also tell you that the total number of supercharges can't be more than 16.
Right. So this is the interacting version of that statement.
That statement.
Yes.
Yeah, but it was just at a very plebeian level.
Yeah.
Suppose you just forget about superconformal invariance. You just look at supersymmetric, and you try to make multiplets of supersymmetric in the little group way, the simple minded way. Okay. Then if you have more than 16 supercharges, you see the way that the massless representations work is that half of the supercharges annihilate the representation. So you've got 8 active supercharges. Then these 8 supercharges group into 4 annihilation and 4 creation. So you have 4 creations each one has spin half. So if you go from 1 to -1, that works. Right? Because, sorry, from -1 to 1. Because 4 raising from take you from -1 to 1. But if you had more than 16 supercharges, then every representation in the game would be forced to have at least one state with spin greater than 1, which no quantum field theory that we know of. So that's.
Yeah, but none of these theories are free anyway,
I
so
understand.
it's very
Well, the n equals 1 versions of them are free.
1,1.
No. The U1 versions.
U1 versions, okay.
But here
1
is-
M5 brane is free.
In 6D,
Yeah.
Shiraz, couldn't we have had more than spin 1 like these antisymmetric tensors or something?
No, by spin 1 I mean spin 1 under any given SO2 of SO6. Antisymmetric tensors by discounting don't have spin. In one plane, choose a particular 2 plane, do a rotation. The spin should never exist.
I see.
Yeah.
Okay, thank you.
Is there a similar statement in 4 dimensions? So the superconformal algebra would exist for any n in 4 dimensions, but
Right. And these guys proved that you cannot have more than n equals to 4. Yeah. Okay, so now let me provide you with some more conjectures. What happens for
it's a bit difficult to see
which thing?
the fact that you don't have stress tensor for higher n's, because it's just the fact that if you start with something in that multiplet you will have, even though it's higher supersymmetry.
But there is no
the
such
multiplet will be
tensor
bigger.
multiplet, stress tensor multiplet. It's a representation theoretic statement.
No, but what I'm saying is that if you start from, let's say, some scalar operator and you keep on acting by supersymmetry generators, you will generate a multiplet. And in
That will be long multiplet.
No,
You want a
short
stress tensor
multiplet.
multiplet.
Yeah, you want to short, let's say, you pick a chiral operator for n equals 5 or n equals 3 here. I don't see why there shouldn't be any stress tensor multiplet in that, stress tensor in that multiplet.
It must have d minus 2 dimension. This is one constraint, and that it must be short. And now representation theory, it's just a representation theory argument.
Yeah, it's a bit difficult to see.
I'm really sorry to ask such an elementary question, but why does a multiplet which has the stress tensor, why does it have to be necessarily short? Short, I assume, means the analog of what it does in lower dimensions, that some fraction of the supercharges annihilate
Right.
states. So, what is the reason why, if the stress tensor appears in a
The
multiplet?
supersymmetry, it should preserve supersymmetry. It should combine well with supersymmetry, with the supersymmetry currents. So that means that some of the Q's must annihilate T mu nu.
And even more, that should be conserved.
Yeah, exactly. Just
So there are
It should
other
become
states.
okay. Just that, so momentum has to.
No, I meant short in sense of supersymmetry.
No, but I think that would
that will follow.
That will follow, because some anti-commutator of Q
Yeah.
will,
Okay.
will be,
Uh-huh.
okay, all right, yeah, I will conserve, okay, thank you. Sorry.
Okay, so the conjecture is that based on all of the examples that we have found, that people have found so far, that LSTs only exist for 1,0, 2,0, and 1,1.
Sorry, just about Abhijit's question, but why it must be something like this. You see, you should be able to get the stress tensor and annihilate it by momentum. Now, if you've got lots of supersymmetries, there's lots of ways of making momentum out of supersymmetries. Sort of lots of different bilinears of supersymmetries must annihilate it.
No, but if I just tune the dimension to be what I want, it would always have a null state there, right?
But that dimension may go below the unit antilope. See, the point will be that, maybe later, maybe.
Okay. Okay, and another characteristic feature of little string theories is that they have a single mass scale. So yeah, I should say something about little string theories, right, before writing all of these things. So little string theories are some theories which behave pretty much like quantum field theories. They are UV complete. Do not include gravity, no gravity. And one very characteristic feature of these theories is that they enjoy T-duality. So this implies that they cannot be local. They cannot have a unique stress energy tensor. So this is our working definition of little string theories.
And can you just remind me, if you take M5 branes and you bring them together in the limit where they're coincident, you get
You take M5 branes on a circle
on a circle.
or NS5 branes in a particular decoupling limit. I will discuss the example soon. Okay, so there are some conjectures about little string theories based on all the examples we have found so far, that they should only exist for 1, 0, 2, 0, and 1, 1 supersymmetry. And they must have a single mass scale characterizing these theories. Let's denote it by the mass of a string, M string. And for energies much less than M string, the effective theory must be an SCFT or free theory.
Sorry, Daksha.
Yes.
This first conjecture, should it not follow from this type of argument, little group argument?
Yeah, there is no conformal algebra, right?
Not conformal, even supersymmetry.
Yes.
Your constraint is that there is no gravity, right? If you have higher supersymmetry, then the multiplet will have higher spin in particular gravity, right? Just little group analysis of a massless field
Right.
would give you gravity and higher
So
spins.
if you have a theory coming from a deformation of a free theory, that argument will work. But most of these theories are
Well, there are-
interacting.
There are
So I don't know how to I don't even know how to formulate this problem right now. I don't know what little string theories are. What are the correct set of observables I should use?
I see. So even the notion of a asymptotic particle is not.
There are no. It can be happen that there are no particles. There are just some strings in the theory on the tensor branch. And if you're not on the tensor branch, then there is a little string. But most of it is interacting stuff with a little string state, asymptotic state.
No, let's say there is a mass scale MS, right?
Yes.
If I go below that mass scale, what do I see?
You see an SCFT or a free theory.
So in the case that you see a free theory is argument will work.
Right. Yeah, but those are only 1, 1.
And in the case that you see in as SCFT, this argument will work.
Okay. Okay, so number 3 would imply number 1. Okay, so now let me discuss some examples of these theories.
Oh, actually, what is the assumption in 3? What else? What is 3 ruling out? What could you imagine that would have been not one of these two?
CFT, non-supersymmetric.
I see, non-supersymmetric. But
No, but this is supersymmetric,
the
right?
whole thing, you're assuming supersymmetry is not broken.
Yeah.
So, sorry, what was the statement? What is
So
the
another kind of little string theory, another UV complete non-local theory could describe the low energies.
No, but that will also have a mass then. And then you can go below that mass.
Sorry, I mean, since it's only an effective theory at these energies, why did it have to be a SCFT?
I mean, it's a prenormalization group. You flow infinitely far. Either you hit a fixed point.
Oh, this is about the deep IR.
Yeah.
Ah, okay. So you're saying what? I could have broken Susie. That's the one.
No, but he doesn't want that. So he's saying that maybe it could have ended up in some non-trivial
Spontaneously broken, right?
Yeah, it could happen that it is spontaneously broken.
spontaneity. That's what you're ruling out?
I'm also ruling out that. Yeah, that there is always a supersymmetric vacuum. Right. So all of these conjectures are not independent. They are depend on each other and imply, some of them imply each other. Okay. So now let me discuss some.
No, what does it mean that LSTs have a single mass scale? What is that statement?
There is a single characteristic mass scale.
What is characteristic? I mean, is this meant to be a precise conjecture?
Yes.
Well, LSTs sometimes have a coupling constant.
On the tensor branch. But on the, there's a coupling constant on the tensor branch, right?
So you're saying that there is no equivalently, you're saying that there is no coupling constant. Is that statement of number 2?
No, I'm just saying the mask, if you look at the number of characteristic mask scales, there is no hierarchy, there's just one.
See, if there was a dimensionless number, then you can take m and multiply it by the dimensionless number, and that'll give you another mask scale.
Right.
So, is this equivalent to saying that there is no dimensionless parameter in the program? If you have two mask scales,
I don't think so, because there can be, okay, I understand, yes, sorry, yes, it is equivalent to saying that.
it's like QCD. You're saying LSTs are like QCD. By choice of scale, they're unique. Okay.
Yeah. Okay. Right. So let me now discuss some simple examples of these theories, and these all examples were found in the second superstring revolution. Okay. So for the first example, I want to start with a 2,0 little string theory, which is T dual to a 1,1 little string theory. Right. So to construct this theory, consider n number of NS5 brains. And let me not specify whether we are in type 2A, type 2B, in both the situations. Then the type 2A or type 2B string coupling constant can be related to the Planck length as follows. And now you take a decoupling, you want to take a decoupling limit such that the closed, the bulk physics decouples from the physics of the brains, which is governed by M Planck, so you want to send this to infinity. To make sure that this happens, let me send G string to 0 and keep M string fixed. Okay, so this implies that we obtain some 6-dimensional theory living on these brains.
And also shows you that there's no dimensionless parameter.
Yes.
Because the dimensionless parameter of string theory has been
Sent to 0. Okay, and this has this is a theory which has stringy excitations.
What is the statement that it's a 6-dimensional theory mean?
The Lorentz group is, there is a group of symmetries.
So if I take a 10-dimensional theory and I put a wave that goes through 4 dimensions, that will also have 6-dimensional Lorentz invariance. Would you call that a 6-dimensional theory?
I want a UV complete 6-dimensional theory. If you put a wave, I will be able to change it. It's not a.
It's not unique, you're saying.
Yes.
Sorry, what was the question?
The question is why do you use that by 6 dimensions? He says he means that it has the Lorentz algebra of 6 dimensions. But you know, if you look at the spectrum of these theories, as he will tell us, it looks awfully like it's a 10-dimensional spectrum.
No, but what did you say about the wave? The other concept?
Suppose I have a 10-dimensional type 2A theory, and then I put a wave that breaks 4 of the 10 Lorentz invariants. I mean, nobody would call it a 6-dimensional theory because the things can move around in all 10 dimensions, but it'll have the Lorentz invariance of a 6-dimension. But that's all you mean. All you mean by 6-dimensional theory is that it has the symmetry algebra is.
No, I mean many more other statements. That it should be UV complete 6-dimensional theory.
UV complete theory with the Lorentz algebra of a 6-dimension.
Lorentz, you mean Poincaré.
Poincaré algebra of a 6-dimension.
It should have a stressed,
It doesn't
this is a stressed answer. Right?
I think that's all you mean. Because as you will explain to us, above a certain mass gap, there's a continuum in this theory. And that continuum looks awfully like it's coming from a 10-dimension origin. So, I mean, there's no. I mean, to call this 6-dimensional sounds a bit fake to me.
Can we think of these as world volume theories sometimes?
Yeah, I mean,
Below the mass gap.
the question. These are words. Suppose you look at the spectrum of the theory. Above a certain mass gap, the spectrum of particles becomes continuous. You know, so suppose you take a 10-dimensional theory and you choose to view it as a 6-dimensional theory, you can always do that. But you get a continuous spectrum of particles in.
So you're saying that this is not truly decoupled? You have doubts
Decoupled
about
or not,
that?
I don't know, that's another issue. But I'm saying, it seems to me that it's not truly 6 dimensional. Because you look at the bulk description, things can move. There's a continuum of states. Anyway, you tell us about it.
No, I won't be discussing those
You won't
aspects.
be saying, okay, so then I want to raise my objection. I
Yeah.
don't think there's any meaningful sense in which this is 6 dimensional theory. This is my personal bias.
Just because of the throat.
Yeah, because the throat is infinite. And there's the modes are labeled by momentum in the throat direction as well as momentum in these directions. And that's not a discrete number, that's a continuous number.
Sorry, well, I didn't catch the third comment, but just simplistically is because, let's say you started in the string theory, where you have NS5, I see you have NS5, but I'm going to take that.
Yeah, so let's take the string description. I'm sorry to interrupt, but the string description is some Wetsuino-Witten theory. Some Wetsuino-Witten theory times an whatever, R whatever. I'm sorry, it's a bit rusty. But the point is that the modes in the cylinder direction don't have a boundary condition at the end. So they're not like they're in a box. That cylinder direction which was the radius of the 10 dimensions, behaves like a continuum direction. So you look at the spectrum of 6-dimensional modes and it becomes continuous after a certain age. And we see from the bulk description that that continuum had its origin in the fact that the theory was 10-dimensional.
And the only part which I'm not able to so remedial is these modes you're describing on the worksheet theory, they don't decouple from some others when you take GS.
No, they don't. They're all part of the little string theory.
Yeah, but this has the 6-dimensional Lorentz group and it's unique, right?
It has the 6-dimensional Lorentz group, but having the 6-dimensional Lorentz group is a very weak notion of being 6-dimensional.
And this is UV complete in 6 dimensions. That's all. I mean, you can formulate this as on a 6-dimensional manifold if you want.
How about the free energy scaling with
The free energy is a strange kettle of fish here. It has a Hagedorn transition. It's on the edge of being well defined. For related. This is a long discussion, which people went through a long time when I was a young man.
That at least scales as if it's 6-dimensional.
It scales like 6-dimensional, but at some point it goes ill-defined. Yeah. And at this point where it goes ill-defined is roughly the mass gap where this continuum happens. So
So are you looking at the theory below the mass gap only?
if you do that, then it's genuinely 6-dimensional.
Is that what you're going to do?
No, I want to look at the whole theory.
Okay, then.
Yeah, but I still don't see why we should regard this as maybe it has hints coming from 10 dimensions, right? But
it's not just hints. See, suppose I took a theory on some non-compact. I took a 10-dimensional non-compact compactification of string theory. String theory and R6 times some non-compact whatever Calabi.
okay.
Would you call that 6-dimensional? R4. Sorry.
No. That Calabia would be.
Oh, sorry.
Yeah.
Non-compact whatever K3 if such a thing exists. Non-compact something or other. Yeah. Would you call that 6-dimensional? If so, then this is 6-dimensional. But I wouldn't call that 6-dimensional. I would call it 10-dimensional. It's a matter of words.
Yeah, but when I will turn to F theory, we will have all of the examples will come from putting it on a non-compact.
Excellent. So then we agree with each other except in the words.
Yeah.
Oh, I see. So in F theory realizations, you have some non-compact version of K3 with a elliptic fibration or something. And you
Even for the SCFTs, they come from non-compact compactification manifolds.
No, but even there's
and you have some PQ, sorry, just to, please excuse me, you have some PQ brains, etc. there, if I were to go to some D brain like limit, is it? And the
It's
exact-
F theory, so there are D3 and D7 brains, no 5 brains.
And there are PQ versions.
Yes, if we go
And
to.
then you have open strings that go between them, right? And you have all in the limit where M string is finite, you probably keep all their excitations. No, it seems
The open
more-
string excitations, yes.
Yeah, then it seems more like what Shiraz says to me too.
I mean, you just see it from the result. You look at the spectrum. Anyway, we don't need to argue.
Okay. Okay. So this theory has stringy excitations of the tension, which is the tension of the fundamental string. This string actually is the fundamental string trapped inside this locus of NS5 brains. Okay, so now if I restrict myself to type 2A, I obtain a theory which preserves 2, 0 supersymmetry in 6 dimensions. And if I restrict myself to type 2b, I obtain a theory which preserves 1, 1 supersymmetry. So these are the 2, 0 and 1, 1 later strings, and they are clearly taken into each other by T duality. So now let me discuss the tensor branch of vacuum of these theories. So my aim in discussing all of these examples is that I want to characterize, I want to look at some general features in all of these examples and take them as sort of conjectures for what the most general little string theories in SCFT, how will they behave like. And it will turn out that in F theory all of those expectations are satisfied. So I will turn to the classification later and show that all those things are actually satisfied within F theory setting. Okay, so to go to the tensor branch, we separate the NS5 branes. By let's say some distance delta x. And now let me discuss the two cases differently. So in type 2a, I would like to keep so in type 2a there are D2 branes which can stretch between these two, between two adjacent NS5 branes, and they will produce effective strings in the 6-dimensional description. So I would like to keep the tension of those 6-dimensional strings constant. So I would like to keep tension of D2 times delta x to be constant, and this goes like in type 2b, I have D1 branes which can stretch between the two adjacent NS5s, and they look like particles in the 6-dimensional theory. And so I would like to keep their mass constant.
This decoupling limit has been taken already or not?
No, I have not taken it yet. So I will again do the decoupling limit. So effectively, when I take this decoupling limit, G string going to 0, I want to keep delta x over G string fixed. And let me call this a modulus U, which will parameterize this tensor branch. One of these moduli.
Okay, you keep MS fixed anyway.
Yeah, I keep MS fixed anyway.
So you want the fundamental strings anyway to remain fixed tension,
Yes.
and you want D2, these
Yes.
new strings.
These new strings. Okay. Right. So what happens when I take all of these u's to 0? So in the 2, 0 case, I would obtain strings whose tension shoots up. They become tensionless. So I obtain tensionless strings. And in the 1, 1 case,
When what? When you take delta x to 0?
yes, when I take u's to 0, all the u's to 0
U's
are these distances.
Yeah.
And in the 1, 1 case, I obtain a non-abelian gauge theory. So we see that the origin of tensor branch is describing tensionless strings in one case, and UN gauge theory in one case. This theory has coupling constant given by the string scale. I mean,
so you're saying the way to think of, suppose I first did it the way you did it.
yes,
That I put all the NS5 branes just together.
Mhm.
And you're saying the way to think of that
is
is
through
as a theory
this.
of tensionless strings.
Yes.
How come I don't see that in the, do I see that in the spectrum of the theory? Or you're saying you can't because it's strongly coupled.
Yes.
I see, thank you.
I'm a little confused, sorry. So you keep delta x over G as fixed,
Yes.
and then you take.
And then I take this too. So I'm saying that from the point of view of tensor branch, you see tensionless strings or non-abelian gauge theory.
I see, and you see it when you go to the M theory picture. Is this right? So suppose we're in the 2.0 version. If I suppose I didn't do the separation, and all my brains are gone. Okay, naively you get string theory with this linear dilaton, and the dilaton blows up in the IR, so you can't trust that. But you can now lift that to M theory, and you get a picture of M5 brains, periodically stacked on the M theory circle, and these D2 brains
Are M2 brains.
are M2 brains, and those are the things that go tensionless because the
Right.
M brains, the M5 brains are on top of each other.
Yes.
Okay, thank you.
But it's the same thing, almost
Same,
similar thing.
yeah.
Yeah. So why do I claim that the
Well,
Where do the fundamental strings come
the
from?
fundamental strings are the M2 brains stretching around the circle. But these are the strings. Yeah.
Yeah, so I will discuss that interpretation in the next example. Okay, so
Just to understand, sorry, so in this limit now, what is happening to G string? So I understand delta x over G string is u, which goes to 0.
G string goes to 0 and M string is fixed.
And G string goes to 0 as well.
Yes.
Okay. So you also have, if you take the 2,0 example just for a moment, you have also got the regular fundamental strings,
Mm-hmm.
and they presumably also are there, and
They are
can
there.
have the tensionless.
Yes.
Yeah. So the M theory picture makes it really very clear. So suppose you've got, in M theory, this thing goes to the M theory circles coming out, and then you've got a bunch of M5 brains separated on the circle. And this delta x presumably will just be the separation of the
M5 brains.
M5 brains from each other. So now you can have M2 brains stretching between two M5 brains, or you can have M2 brains going around the circle and coming back to the same one. The M2 brains going around the circle coming back to the same one is the fundamental string. And the M2 brains going between two M5 brains is this tensionless string. And the thing that will become tensionless is put them up together.
So the fundamental strings are still tensionful.
Yeah, because that's just MS. MS is being held fixed.
Yeah. So I will make the M theory viewpoint explicit in just a few moments.
Why do you say that G-square angles is Ms?
Yeah. So because these strings look like double bosons in the theory, and the mass of the double bosons is, and these are BPS double bosons. So you have double bosons which are BPS, and this implies that their mass should be equal to G Young-Mill squared times the modulus.
Sorry. No, I was just going to say, if you did S duality in 3D, your NS5 would become a D5, and this would be
Yes.
fundamentals, and then you'd get Young-Mills.
Yeah.
Exactly. That's
But there is a dynamical scale associated to it.
To
Gauge theory.
yeah, so there is M string squared associated to both of these. I'm just describing later string theory from the point of view of branch of Vacuum, which becomes
So it becomes free below the scale, then the effective description is Yang-Mills. Above the scale, Yang-Mills description breaks down, and the correct description is needed.
You are taking equally separate lengths, right?
no different ones. I just wanted to make the argument. No, they can be different delta x's, different
But all
u's.
delta x's are held fixed.
Okay. But so there will be different views.
Yeah, there are different u's. I take all of them to 0. U's to 0.
All the users.
Yes.
Otherwise we'll get some product.
Well, but even if
Yeah.
one u is taken to 0, you'll have one tensionless.
Right. So there will be some u in the 1,1 case. There will be some u n minus k. Right?
Yeah, they are different branches of Vacuum.
Only coincide.
Yes. So there the SCFT becomes a lower rank SCFT times a free theory. Okay, right. So what happens at energy is much below the string scale.
And sorry, in this, so we discussed the 2,0 case a lot. In the 1,1 case, Once we go to the d5 brane description, this delta x will just become the value of the scalar, the Coulomb wave of the scalar, right? That will be n fixed.
Right.
The 2,0 little string theory below MS is just the SCFT.
Yes. So
M5 brane SCFT.
yes.
If they already get, yeah.
So when I take at energies much below ms, I obtain, because I send this string scale to infinity, I obtain a theory of tensionless strings, and this is the 2, 0 SCFT. And for this, I obtain
Free
what the-
variables theory.
yeah. So I obtain a 1, free 1, 1 super-Young-Mills theory.
But it's only valid when a pattern energy is much less to ms.
Yes.
So it's essentially free. So that was a distinction at the beginning. Either goes to well forward or free.
And I'm sorry, you might come to this, but you said that the theory has T-duality, which it should because it has strings, but just to help me, you mean now put it on a circle?
Yes.
That's what you meant,
Yes.
right? Okay, thank you.
And the theory at circle size, the 2A theory at circle size R1 is the 2B theory at circle size ms by R1.
Yes.
Which makes it clear that there's no stress tensor. Because stress tensor in which space.
Which momentum? Oh,
Yeah,
whatever.
yeah.
Mhm. Right. So I can take this 2, 0 as CFT, and this has a a tensor branch of its own. On the tensor branch, the tensionless strings become tensionful, and at low energies, you just find the theory of free tensor multiplets, free 2, 0 tensor multiplets. Okay. So
It's kind of like a cyber
sort of. Right?
More
It's like a
inverse.
Coulomb branch. Tensor branch is like a
More
Coulomb
like
branch.
X square. It's so trivial. Yeah.
Yeah, but there are no monodromies or something. There's no cyber-Witten theory in 6 dimensions. Okay. Right. So let me present the different perspective, the M theory perspective on these theories. And this will uncover some more general characteristic features of these theories. So let me first remind you the duality between type 2A and M theory. So I just want to look at the 2, 0 case in this case. So type 2A is M theory on a circle of radius r, and the parameters are mapped to the Planck length and the radius such that so when I'm writing Planck length now, this is the 11-dimensional Planck length. And our picture of NNS5 branes is mapped to a picture of NM5 branes sitting on this circle of radius r. The decoupling limit becomes the following, that r goes to 0, Planck scale goes to infinity, and the following combination of r and m Planck is fixed.
This is just the tension of the
Right. So
fundamental string. MS.
this is the tension of an M2 brane wrapped around the circle.
Also known as fundamental string.
Yes.
This is just formula.
Yeah.
Just
Yeah,
Mhm.
it's just
without any GS. Doesn't have to use the string.
correct.
Okay, and then, sorry, and then what is that, 4 NST?
Sorry, NNS5s.
Oh, N, okay, okay, got it.
Right. And so this is our fundamental string. And the tensor branch is, you can move to the tensor branch by separating the M fibrils. So now we see that there is a compact direction in the 2, 0 tensor branch, where the size of this compact direction is set by M string. And of course, you could move the M fibrins in the transverse directions as well, and you would obtain some part of the 2, 0 tensor branch which was non-compact. So this is some key feature when we come to 1, 0 theories. So let me phrase it in a 1, 0 language. So we know that SO5R is the same as USP4R. So there were 5 directions in which the M fibrins could move. One of them was compact. And I can write USP4R in terms of, I can look at an SO4 group of SO5, which breaks into an SO2 and an SO2, which I'm calling as USP2s now. So there is a subgroup of USP2L and a USP2R. This is the SO4 subgroup inside it.
USP2 is the same as SU2.
Yes. So this is the same as.
Some
Right.
people call that USP1.
SP1,
There's a standard confusion when it comes to SP groups.
All of my USPs are even. Okay, so this setup already broke our SO5R symmetry to SO4R symmetry because of this compact direction. And there is a particular subgroup, right? There is a USP2R which is preserved by this theory. And this is also the R symmetry which is preserved by a 1, 0 supersymmetry. So yeah, so this compact part of tensor branch can be identified as the 1, 0 tensor branch inside it of a particular 1, 0 supersymmetry. So the claim is that 1, 0 tensor branch is compact and the size is set by the string mass scale.
Sorry, I didn't understand this. Can you say that again, please? What? I understood your.
Yes, so there is a 1, 0 supersymmetry.
Yes.
Which is tied to this compact direction.
Tied to meaning there is a
So,
breaking which preserves that one, preserves something that looks like the 1, 0 part, preserves something else as well.
Right, so the claim is that if I were to choose this 1, 0 supersymmetry and view my theory as a 1, 0 theory,
Yes.
then the 2, 0 tensor branch will split into 2 branches, a 1, 0 tensor branch and a 1, 0 Higgs branch.
Okay.
And this compact direction is the 1, 0 tensor branch.
So it's just one dimensional?
Yes, it's one real dimension.
One real dimension.
Yes. So tensor branch does not have a complex structure in general. Okay. And this 1, 0 tensor branch is analogous to 4D n equals to 2 Coulomb branch in the sense that this preserves the R symmetry, preserves 8 supercharges and R symmetry, 8 Qs and R symmetry. And we also see one more thing, in the M theory setup, the little string is not really separate from the strings that appear on the tensor branch.
And so what is the definition of a tensor branch?
Of 1, 0 tensor branch?
Yeah. What do you mean by a 1, 0 tensor?
Where you give VEF to tensor multiplet scalars.
And tensor multiplet is the same multiplet that contains what?
Yeah, I will review this. It contains a B field, a chiral B field, and a single real scalar.
The sixth branch is the separation in the non-compact directions.
Yes, the 4 non-compact directions.
So I should think of this roughly like the vector multiplet. The tensor multiplet is sort of like the vector multiplet of 4-dimensional gauge theory.
Yeah, the B field vector multiplet.
Yeah, and the Higgs branch is like the hypermultiplet.
Yes, but there is a separate 1,0 vector multiplet as well, which contains gauge field. So you should not confuse between these two.
I see.
So in string theory, tensor branch is not to be thought of as like separation of n square branes.
Which tensor branch?
No.
1, 0?
1, 0.
Yeah, it's not the separation of NS fibrils.
And what is it? Is there a string theory description of it?
Yeah, this direction dualizes to RR0 scalar, right? So it's the wave of that scalar. Okay, right. So from this viewpoint, we see that the little string is not something very special, or at least on the tensor branch. This appears as a linear combination of the tensor branch strings, a particular linear combination of the 1, 0 tensor branch strings. And now if we take the limit r going,
Sorry, so whatever this thing is, it should have some matrix structure.
this thing,
Yeah, I mean, it should have n different eigenvalues.
yeah, this has a metric which governs the kinetic, the scalar kinetic term.
No, the matrix.
Uh,
I mean, separation in a circle in D branes is eigenvalues of a Wilson line.
right.
And that makes sense because there are n different eigenvalues of the Wilson line, so there are n positions. What did you say about the RR0 form? I didn't understand that. There should be n different positions of these branes, all encoded in string theory. What
Right, so I'm looking at the diagonal part of it.
But there's an open string RR. So closed string is that there's no n cross n matrix.
Yeah, I don't think there is an n cross n matrix here.
Then what does it mean that the position?
So if I don't have any branes, right, this compact direction becomes the RR scalar of type 2A.
Okay.
And now if I put a M5, this becomes an NS5 at that location, a single M5. Sorry?
Type 2 is the gauge field. The D0 brane will couple to a gauge field.
Yeah.
Right? That's
Yeah.
what I'm a bit confused. Is it just the matrix structure?
On something like that. Yeah.
Sorry, RR1 from there.
It must be something. But it has to be something to do with the. I mean, something that's not there just in the clue. Yeah. Without the brains.
Yes.
Yeah, you can move just individual.
Yes.
Yeah, I mean, you can say that the NS5 brane theory contains 2, 0 tensor multiplet, and one direction is compact, which is not seen in the geometry. It's just one of the scalars.
One of the scalars, and there's some sort of matrix structure, something like that.
No, there is.
Is there a gauge field in that 2, 0? Is there
Not a gauge field. It's like.
No, NS5s do not have a matrix structure, right? The motion of NS5. So this
I
scalar
understand,
also.
but there have to be n separate things for each of the NS.
Yes, n of them, diagonal ones only.
Diagonal in what?
I mean,
Yeah, that's.
in the matrix analogy.
Yes. Yeah, except they're not chat pattern.
If we have relative separation between the NS5 branes, how is that encoded to this diagram?
Yeah. So roughly speaking, there's some structure which is the diagonal elements of a matrix, whatever that means.
Yes.
And then each individual diagonal element is the position of the individual NS vectors. But what that is, I'm not completely clear. It's some world volume thing. And it's mysterious because the world volume theory of M2, M5 branes itself is mysterious, and then when you put it in a circle, it's more mysterious.
Right, but when he wrote the tensor branch modulus U, so it's proportional to the separation between two NS5 branes.
Two M5 branes.
Sure, okay. Two
No,
NS5 branes
it's
are
important
almost-
because there's NS5 branes can't move in the M theory circle because there's no M theory circle for NS5 branes.
How many tensor multiplets are there?
1 2 comma 0 yeah 1 multiple 1 tensor multiple in the
All
sorry
tensor
pl-
branches,
no,
n of them.
yes valued in
When you
u1
put that
to
all
the n.
together, you know from free energy that there should be something like n cubed. It's a very mysterious structure.
So I mean, this is a good point. So if you have n of these NS5s coming together in two-way, you have a scalar in that 2, 0 tensor multiplet which has some which can take n independent values in the whatever branch tensor branch.
Mhm.
But presumably the tensor field doesn't have any such structure, right? They're part of the same multiplet.
Yeah, this whole business of trying to formulate a non-abelian tensor multiplet theory has never had any success. So all we understand really
I see is the
is the Coulomb
whatever
branch,
it's
yeah.
called. I see. We don't really know the structure of the non-abelian geometry.
Yeah.
Okay.
So in that theory, whatever it is.
Okay, so now if you want to go to the 2 comma 0 SCFT, you take the limit r going to infinity and m Planck going to infinity simultaneously. This gives you 2 comma 0 SCFT, and in this limit you see that the compact direction decompactifies. So right, and you obtain SO5R symmetry. Your symmetry enhances. Now, based on this, there is a sort of slogan which has no physics context, but which is always true. I mean, this was helpful in for us to classify Little string theories in F theory. So let me mention it anyway. So the slogan is that SCFTs are like finite quivers in Lie algebra theory, and little string theories are like affine quivers. You can go from SCFTs to LSTs by a process of affinization. So in this picture, what this means is that if I consider each block,
You have to explain the slogan in a dumbed down way first. I'm really sorry, and you can do it later. I don't want to, but I mean I know what quiver gauge theories are, but I'm sorry I don't know what affine quivers and
yeah. So I'm doing it in this example. So in this example, if let me draw this properly. So suppose we have something like this. Then to each segment, I associate a node of a quiver, and for every NS5, I associate an edge of the quiver. So the quiver that I obtain is like this. And this is a quiver which will be associated to a Dynkin diagram of type, of an affine Dynkin diagram of type A3, affine.
Very strange. You're associating a node to the spaces in between the S.
Yes. So the reason will become clear in the next example.
Okay.
So I will have some gauge theories living to these on these edges here, and which I want to put on the nodes here.
Okay.
And if I decompactify this direction, I have M fibrins like this. So the quiver that I obtain is something like this, with probably some infinite length things. And you see that you can go from, this is a Dynkin diagram of type A3, a finite Dynkin diagram. And you can affinize this to get here.
Oh, I see. It's the affine version of the Dynkin diagram.
Yes.
So, and what does affinize mean?
I mean, it is just a slogan. There's not much precise
Yeah,
content
but
here. You just join these
join.
two and make a new node. So if you forget these nodes, you're adding a new node.
And a new line.
Yes.
Dynkin diagram versus extended Dynkin diagram.
Only vaguely. Some point in my education, I've come to these things.
The chapters of Georgia, my eyes glassed over.
Okay. Now let me do another example, this time a 1, 0 example, where all of these features that I have been highlighting will become more apparent. So a particular example of a 1, 0 little string theory and SCFT. So now let me take type 2a theory and put it on a circle. Just like we were putting M5 branes on this circle, now let me put some NS5 branes on this. And let me wrap D6 branes around the circle. So I have n D6s wrapped on this whole circle. And the radius is R. Let me use k D6s and n NS5s.
This circle is in 10 dimensions.
Yes. Okay, and again I take the same decoupling limit. G string goes to 0, M string is fixed.
This is M series circle, right?
No, this is a type 2a circle. I'm in type 2a now. Yeah. And the D6 branes are wrapping the circle.
So this is not a tensor branch.
No. I mean, this will be the tensor branch of 1, 0 theory. Again, I have this modulus u, which is delta x over G string. I keep this fixed. And this implies that M string cube times delta x over G string is fixed by combining the fixed quantities. So what is this that I'm keeping fixed? This is the tension of D2 branes wrapped around, wrapped between these two between these NS5s, stretching between these two NS5s. So tension D2 times delta x. So it's the strings coming from the D2 branes that I'm keeping fixed.
So this you were calling the Higgs branch, right?
No, now I'm in 1, 0 case, so there is no. Yeah, so the Higgs branch would still be the transverse directions.
So that's a 3-dimensional Higgs branch.
Right. And the fourth dimension coming from the M theory.
So you
One.
swapped.
Yes.
Swapped M theory circle.
Yes. Yeah, Higgs branch will always be 4n dimensional. Okay, so we are on the tensor branch. On the 1, 0 tensor branch, I obtain a theory which is described by the following curve. A gauge theory, because for every D6 I obtain a gauge field living on each of the segments, and the strings stretching between the branes going through the NS5s give you bifundamental matter between them. So I obtain a very conventional looking gauge theory.
Sorry, I missed the last thing. Could you say the last thing you said again? How do you get a gauge theory?
You obtain a gauge field for each segment of D6 branes and the bifundamental matter between them. Okay, and the Yang-Mills coupling
The
is,
reason why we get only gauge fields is that the NS5s cut the D6 branes.
yes, so each of them is independent.
Oh, yeah, okay. So the strings that go from one piece to the other through the NS5, that's the one you said.
That's the bifundamentals.
And D6 branes can end on these NS5 branes.
Yes.
So they can move
They're
separately
ending.
and so-
Yes, they can move separately. No, sorry. There is a RR charge conservation at the location of NS5 because the brane has very high dimension. So in this case, you will have to move them together.
I see.
The number of D6 branes from the left and the right must be equal
I see.
for
It
RR
would
charge.
pull it too much, you're saying. It would pull the NS5 brane too violently.
Yes. I mean,
Providing the Coulomb
The
branch.
number has to be equal, but can they split on the NS?
Yeah, yeah.
no, but the NS5 is embedded in the volume of D6. So let me write it down. NS5
Okay. They all
is
they
from-
share common word. There's no issue.
Oh, I see, I'm sorry, okay.
this is the sixth direction.
Okay, yeah, I'm sorry, okay.
My fault.
Right. So there is no Coulomb-like motion, Coulomb branch-like motion.
So there are also some massive strings also, right?
Yes. which are coming from D2 branes, and I'm keeping them fixed.
D2 branes stretching between the NS files.
Yes. So the Young miscoupling will be given by just dimensionally reducing the D6 brane theory on the segment, and this again turns out to be M string cubed U. So we see that the tension, the Young miscoupling is the same as the tension of the string. They're controlled by the same parameter. So this is another general feature that I want to highlight. And another curious fact is that the strings are D2s which are inside D6s, and so they must be instantons of the D6 brane theory. And when you go to 6th dimension, they again become instantons for these gauge groups.
So instantons, I see. So if a string is stretching between one guy and the other, it's an instanton in that gauge theory.
Yes.
Of that segment.
Yes. And the little string becomes a linear combination of the instanton strings. This tension of little string is M string cubed R over G string. And you see that the tensor branch is compact again. So tensor branch is compact and has size given by R over G string. So now,
sorry, if I thought of this as the M theory circle rather than the string theory circle, sorry, this is just an elementary question. What would this M theory description of the D6 branes be, please?
it would. So if you just naively lift it, you obtain singularity, the top net singularity in M theory.
Yeah, because all his language is as if it was the M theory. He's calling these the string stretching between these bits.
So yeah, so you first want to lift it to M theory, right? Then you obtain a singularity with M5 branes wrapping it, right? And you have you have fibration of a torus, right? There is this one circle and another one, and you want to reduce it on the other direction,
Yes.
back.
No, I mean let's look at it as M theory. M theory in 11 dimensions. Now there are two circles. There's this and the M theory.
Right. So
And if I were now if I were to reduce on this circle, what would that be in string theory?
Right, so-
D6 in a sense is a KK monopole, but now you wrap it and then you go up and you want to think of that as the M theories.
So now I reduce on this rather than that.
Yeah.
That's more in tune with your language than the previous part, right?
It's just someone else. I don't know what it's called.
But this description is anyway after reduction on two circles.
Oh.
right. So this is NS5s on a singularity. You
Sorry?
put NS5s on a singularity.
That would be the effective description.
And no, this is the full description. NS5s on AK minus 1.
If I interchange the two circles, that's what.
Yes,
it would be.
yes.
What was K? I'm sorry, K. Was the K D6?
Yeah, the number of.
Yes.
So that's how it's tied to the gauge group, I guess.
Yeah.
Also.
Mhm.
Okay, I understand.
What does the instanton number mean?
The integral of f wedge f,
Yeah. So that would be what?
the number of D2 branes in between. Okay, so now if I look at this setup,
Sorry, I'm a little confused about something, which is, I understand your D2 brain stretching between your NS5s,
Mhm.
and then, okay, and then, but then when you say they're instantons, they are instantons in which gauge group? You have effectively gauge groups at the center of your thing, right?
The gauge group,
The segment.
this stretches between.
this gauge group also stretches between the two NS5s. I mean, there is the 7-dimensional gauge theory, which is reduced to 6 dimensions, right? So, and D2 branes are 3-dimensional objects which are instantons inside the 7-dimensional theory. After dimensional reduction, they are both, I mean, they become
don't
sinusoid.
live on crosses, they live on segments.
Yeah, they live on segments, I
And
understand.
the D2 branes also live on segments. So there's a one-to-one.
I see. Usually the instantons are present even when the gauge theory is not. When K is 0, you still have D2 branes.
Yes,
But now you want to think of D2 branes as instantons of this UK theory.
yes. You can, I mean, I'm just saying you can do it because it will be part of one of the classification procedures. So I want to highlight this. Okay.
I see, you mean you still have the NS files when K
When
is
the-
0?
Yeah, and the D2 branes will stretch still.
Okay.
Yeah, that is true.
But it's like 0 branes exist even without 4 branes. But in the 4-brane description, they exist.
Okay.
This gauge group you were missed something. This gauge group you were inventing as a bookkeeping device, or is it really there? I'm sorry.
It's what
It's
breaks
there.
it down to 1 comma 0.
Yes.
Without it, there would be the 2 comma 0 LST that we
Yeah. So it's a different
Not
theory.
compactification.
It would be a compactification of it.
Yeah, yeah.
Yeah.
I mean, if I just have NS5 separate, where is the gauge group actually in terms of the dynamics? I have NS5 branes separated. I'm missing something.
If there's no D6 brane, there are no gauge.
Okay. Yeah. That's what I'm confused about. Okay.
Now you've add the gauge D6 branes, there's new dynamics, there are new gauge groups, and as Abhijit pointed out, some phenomena that were visible even without the D6 branes have a purely gauge theoretic description, namely the instants.
Okay. So the gauge group is just whatever corresponding to AK minus 1, SUK or something, right?
Yes.
Okay. Now that's just the D6 gauge.
Yeah.
Okay.
Mm.
I'm with you now.
Okay. So now if we look at the setup at low
Many
energies.
copies of SU.
Mini copies.
One for each segment.
That was the point. Yeah. Okay. Thank you.
So at low energies, the system looks effectively decompactified with NS5 branes being close to each other. We have KD6s, and we obtain a theory which is described by a QVer of the following type. So I have QVer in the shape of a finite Dinkin diagram with some flavor symmetry on both of the ends.
You said something, I missed the word. At low energies, what is this?
Effectively, the system decompactifies if you're near the origin of the tensor branch.
So you keep the branes near to each other,
Yes.
but
Yes.
yeah, okay.
Right. So you obtain a theory like this, and this is an example of an SCFT. Once you take all of the branes to each other, you obtain tensionless strings again, and so this is a 1, 0 SCFT described on the tensor branch. And now you again see this process of affinization, that if you take this SCFT, you affinize it, you obtain the little string theory.
How do you see the emergence of a scale after affinization?
The length
No,
of the
it-
circle.
No, but just purely gauge theoretic description.
Yeah, this is just some bookkeeping process. It's just some words. There's no physics content there. I'm saying that you take one theory and you can go to a little string theory by a process called affinization. There's no map between the parameters. I'm just saying the tensor branches map.
Because
Very naively.
here the branes are already taken to be together, right? When you write down this gauge theory description of the SCFT.
Yes. No, they are close by.
Well, you have taken I thought you have taken the scaling limit in which you have sent the string mass to infinity.
Yes.
Right?
Yes.
And then this is the gauge theory description.
Not the string mass to infinity. Sorry, the length to infinity. String mass remains fixed. The radius goes to infinity. So the D2 brane which wraps the circle has infinite tension now.
But that's what he's calling the string mass. He's thinking, imagine that you decompactified on that, you compactified string theory on that circle, then the string mass would go to infinity.
Right.
that's your low energy limit, right? I mean, even in the earlier discussion when you described low energy limit, essentially E was much less than string mass.
Yeah,
It must be that this thing has, it must be that the beta function for the overall SUK, the center of mass SUK is not 0. Right, because it's like the overall SUK whose G squared diagonals is the size of the cell.
Right, yeah. Overall U1 even.
Maybe even the U1. But I think the whole SUK.
Okay. Right, so now let me collect all of the general features that have come in these examples into a list.
Sorry, just one more thing. It must, of course, this overall SUK must be going free in the D by R. So you've got a mass scale set by its G squared diagonals, below which it's free, and then you get back this description. But above that,
So do we have to end soon?
yeah, we should end. If we want to eat lunch, we should end.
Okay.
ICTS has got
Okay, so before moving on to classification, let me just collect the general features into a set of conjectures. So because from the field theory point of view, these are just conjectures, and they have only been satisfied in F theory examples. Okay, so the first thing is that every 6-dimensional SCFT or little string theory has a tensor branch of backward. I should say 1, 0 tensor branch. Non-trivial. So this is the vacuum which preserve USP2R symmetry. The low energy theory on a generic point on the tensor branch is a gauge theory coupled to some 1, 0 tensor multiplets.
And this is you're looking at the case where it's 1, 0 and not 2, 0.
All SCFTs, because in that case, in the 2, 0 case, the gauge theory part will be absent.
Yes.
It will be trivial. Okay.
This bifundamental line is some sort of a tensor line. This bifundamental line.
Yes. Yeah, I mean, so each NS5 was giving you a tensor multiplet, but then the overall tensor multiplet was decoupled, overall motion of NS5s.
But no, in this non-affine case.
Then also the overall one is decoupled. Right, so whenever I am calling tensor branch, now I just mean this 1, 0 tensor branch. Okay, and the tensor branch is compact for little string theories, and tensor branch is non-compact for SCFTs.
Wait, so it's just to understand now the bifundamental matter from the gauge theory description, was that in a multiplet that included a tensor?
No, that was in a hyper.
That was in a hyper.
Yes.
So wait, I'm sorry, I'm getting confused.
Yeah, I didn't understand that. I thought there is a tensor multiplet.
Yeah.
Say that each of these, maybe overall is decoupled, but each of them has.
Yeah, there is a tensor multiplet as well. It's just the motion of NS5s.
So the D6 brane has just a vector multiplet. Is this right?
Yes.
Okay. then the remaining multiplets come from the NS5 ring, so the string stretching between D6
Yes.
rings across NS5.
Yes.
One of these is the bifundamental matter.
Yes.
And in addition, there's a separate multiplet,
Which is just the motion of
which
NS5.
is just uncharged. Under
It has nothing to do with strings and D6s.
So it's uncharged under the gauge group.
Yes, it is uncharged.
Okay.
But there will be one for each. It will depend on the number of NS5.
Right.
And the size of tensor branch for little string theories is controlled by M string of the story.
This description is not really addressing the genuine 2, 0 part. This is essentially addressing the decoration of the D6 brains.
Which description? The gauge theory description,
Yeah.
you mean?
Because
But this is the
using-
tensor branch of the.
See,
of the
using
theory.
that description, I cannot get any insight into the 2, 0 physics.
If you can study infinite coupling, because the coupling of this is controlled by the tensor branch modulus. So, right, and if you take the tensor branch modulus to 0, the gauge coupling shoots up. There was a,
Oh.
right, so the gauge coupling was just the tension of brains, right, M string cubed by,
The distance becomes 0, gauge coupling is infinite.
this was 1 over G Young squared.
But why does that help? Why does gauge coupling shooting up mean that there's no gauge? So yeah, so what?
This is a strongly coupled theory. Gauge theoretic techniques are not going to be helpful at the conformal point.
Okay.
I'm just saying it becomes infinitely strongly coupled. So-
No, but Abhijit was asking, suppose I wanted the description without the D6 brains. I wanted the theory without the D6 brains.
I see.
Can the theory with the D6 brains help us learn about the theory without the D6 brains?
Yeah, so you can catalog the answers in terms of K and N, in terms of the number of brains, and just send it to 0.
Continue to 0.
Yes.
I see. Okay.
Okay. Right, and on a generic point of tensor branch, some things happen. So first, there are only massive strings.
Sorry, what is it? I'm sorry to interrupt.
So the claim is that on a generic point of tensor branch, you cannot find any massless strings, any tensionless strings. Okay, and the number of the strings, string excitations in the theory will be equal to the number of tensor multiplets, or the number of tensor multiplets plus 1 for SCFTs and little string theories respectively. So each string is charged under some tensor multiplet. So there are no uncharged strings in these theories.
So this is the, all this discussion is for E much less than NS.
Yes, on the tensor branch of vacuum. Yes.
So we never see the fundamentals of the massive fundamental string.
Yes. Yes.
E strings. So strings are these D2, what were the D2 brains in your previous example?
Yes.
And they're charged under some tensor multiplet. Can you roughly, what is the effective interaction of the tensor multiplets? I mean, what does the statement mean?
So there is
Charged under a tensor multiplet, how does it? Oh, you mean
so
the
there is a B
field,
field
you
which
charge.
couples to
Okay.
this. And finally, for SCFTs, respectively little string theories, there exist exactly 0 and 1 string whose tension is invariant on all tensor branch.
Sorry, Lakshya. Suppose you just had one NS5 ring and k d6 primes. In this case, is it possible to write down the effective low energy action? I want to see what this tensor multiplet is doing. It's clear what the gauge.
How does it
open-
couple to gauge theory, right?
Yes.
Yeah, so I want to describe this after this. I just want to move on to the coupling between tensor multiplets and gauge multiplets.
Right.
Yeah, but that will probably be tomorrow.
Tomorrow.
So I can say some things, right? This is from a paper by Seiberg, where he initiated these things. So there is a coupling like this. This is a tensor multiplet scalar, and you have a coupling of the following form: trace f wedge star f integrated. So this acts as the modulus of phi acts as an effective gauge coupling, and there are couplings of the form b wedge trace f wedge f, which come from supersymmetrizing.
So the first thing is the thing that ensures that the string has mass that's proportional to distance.
Yes.
Okay, and the second thing then.
String has a mass.
F wedge f was the string.
F wedge f was the string, yes.
And we want, if you have a non-zero f wedge f, we wanted to have a mass that's equal to the distance between the two ns vibrations.
Yes.
So that phi there will be roughly that distance, and that coupling will ensure that.
Yeah, yeah. Right. So these are some conjectures which I hope can be formulated, and some of them possibly proved from directly from the field theory viewpoint, without the help of any string theory.
And this is the only coupling of there's no coupling between the tensor multiplet and the bifundamental matter.
There is a coupling coming to, it's the Green-Schwarz anomaly cancellation.
Can you roughly?
Yeah.
write?
Right,
With some
so-
higher irrelevant couplings.
Right. So B wedge.
We can do it next. That's okay.
Mhm. So it is precisely this coupling, right? I think. Right. So there will be some this coupling.
Wait, that's between gauge field and B. What about the bifundamental matter?
Okay. No, there is no coupling with bifundamental matter.
There's no coupling with the bifundamental.
Yes.
Okay, great.
So what string is that in these examples?
Which-
Which has invariant tension on the whole host.
Yeah. So for the little string theory, that's the little string. That is the defining
The
property of little
linear
string.
combination of some of the
Yes. So this can be taken as the definition of the little string, but now you have to prove that there are not more than one.
The guy doesn't
Sure,
know
sir.
all the way around.
But aren't the D2 bits like cut? So you're saying you align them.
For the SCFT, there's no such string. For SCFT, there's zero string.
Right, so this is the one with the circle. The
Yeah.
LST is the one with the circle.
Exactly. The LSD is the one with the circle. This is the D2 grid that goes all the way around.
Right. So but because the NS5 brane is cut, so it's essentially pieces of D2 branes aligned such that they all go.
So it's an instanton in the overall SUP. Center of mass SUP.
And why is its tension invariant? Because
Because it's set by the size of the circle. It doesn't care how it's divided up.
No.
Okay. Okay. Questions? Since there were no questions at the talk.
Actually, I have a,
Yes.
it's just a clarification, but what you call as the little string is the one whose mass does not, whose tension does not go to zero as you take the tensor branch moduli to zero, is it?
Yes.
Yeah, that's set by the size of the circle, not the distance between it.
Right. But as, okay, but it's, so when we take this E much less than MS limit, this string is still relevant for the physics,
E is what?
the energy scale.
Only as a higher dimension,
Not relevant.
higher dimensional term, right? It's something which has been integrated out.
You see,
Yeah.
in the low energy limit, you get back to the SCF. That's the limit at which you don't see
Okay.
the
This
circle.
is the ordinary opening.
Yeah, I'm just saying higher dimension operators will.
Correct, correct.
Yeah.
Sure.